evening and welcome. I am Nigella Hilgarth and I'm the Executive Director of the Birch Aquarium at Scripps Institution of Oceanography, UC San Diego. And it's a great pleasure to see you all here tonight, see so many friends of Scripps Institution of Oceanography and the aquarium. And it's my great pleasure this evening to introduce our speaker, Dr. Miriam Kastner. Dr. Kastner was born in Czechoslovakia and received both her bachelor's and her master's degrees in geology from Hebrew University in Jerusalem, Israel. And she then received her doctorate in geosciences from Harvard. And she has received so many awards and honors and served on so many national, international advisory committees and held a variety of academic and administrative positions that if I began to read even a few of them, we'd be here a long time. So I just, in summary, she has a very distinguished scientific career and a very distinguished administrative career. I'm just going to read you a very few of her honors, and they include a Fellow of the Geological Society of America, the Hans Petersen Medal, the Royal Swedish Academy of Sciences, a Fellow of American Association for the Advancement of Science, and a Guggenheim Fellow. She came to Scripps in 1972, and she conducts a variety of lab research as a full professor here at Scripps, and she investigates such diverse subjects as the geochemical history of seawater, submarine mineralization processes, the mineralogy and geochemistry of marine sediments, and the nature, origin, and fluxes of fluids in subduction zones. And she's published over 135 papers in refereed peer journals. And she also teaches many classes here at the university. And she's participated in, I think, at least 20 ocean expeditions and was chief scientist on several of them. And I was talking to one of our professors here at Scripps earlier this evening who has been privileged enough to be on several of those ocean expeditions with Dr. Kastner, and says that she has more energy and works harder than anyone else he's ever been to sea with in his life, and he's been on a lot of trips, that she is just a phenomenal scientist at sea and really puts the rest of us to shame. So please join me tonight in welcoming Dr. Miriam Kastner for her talk entitled Methane Hydrates, Natural Hazards or Natural Resource.
Thank you. Thank you, Nigella. Can you hear me? Okay. Thank you for the nice introduction, very generous introduction. And I will go immediately into the talk because I'm trying to cover a lot of things tonight with you. As you see, this topic there is not exactly what I'm going to do. I'm going to talk about this general outline. We're talking generally about methane hydrate or gas hydrates. It's a class rate type structure. When you don't know about a class rate type structure, it's a structure that has a host and then it has guests. It's like in a hotel that people are coming and going. So the structure of hydrate is basically water, ice, and different gases come in and out, and the hydrocarbon gases are the host gases. So I'm going to talk a little bit about what the hydrates are and why do we care about them, how important they are. The occurrence in nature, where do they occur? Are gas hydrates susceptible to climate change? You will see why we worry about it with respect to climate change. And is there any evidence in the past the hydrates were really susceptible to climate change? And what about resources as a new source of energy? Everybody's talking about resources. I'm going to talk very little about it. I'm going to emphasize my talk about the climate change and about geohazards. These are the two topics I'm going to particularly mention tonight. Let's first look at the gas hydrates. I already told you what it is. Here you see the structure, and these red ones and the white, these are waters. And that is the gas. In this case, it's a methane, but it could be ethane, propane, or CO2 as well. And the real amazing thing about this hydrate structure, the real amazing thing about the structure is the storage capacity. If you take one centimeter cube, or if you want to talk about, inches, whatever you want to talk, 1 cubic inch, and you decompose it, it looks like ice, and you decompose it, the amount of gas in such 1 centimeter cube is 160 to 170 times the volume of the hydrate. So it stores a lot of gas in a small area. And it also is stable at low temperature and pressure. I think I will stay here because I have to move the computer. Okay, here you see hydrates. That's how they look like. They look like ice. That's water. But the difference between ice and that is if you take a match, it burns. Here you see the fire. And that's methane. It's beautiful fire, very pure, and it forms CO2. So that is, in terms of future of energy, that is what we will be talking about. Here you see an example. Recently, many countries got very interested in it, and that happened in Korea. They found these gas hydrates, and on the ship they got so excited, somebody just took a match and they just looked at it, how it burns, because it's the first thing you do when you find hydrates, actually. Okay, now, everybody has to try it out. When I teach a class, I do the same thing in the class. We just show them how it burns. In terms of structures, there's more than one structure. These are the two main structures. And the difference is that the cages, the size of the cages, and the size of the cages determines what kind of gases can enter into these hydrates. Structure 1 is particularly the methane hydrate and the CO2 hydrates, this structure. Here's the structure 2, which can accommodate, has larger cages also, can accommodate the higher hydrocarbons. When we have in oil terrains, for example, in the Gulf of Mexico, there's a lot of structure 2. There is this third type of structure H, which has even larger cages. So all kinds of gases can form hydrates. And today I'm going to talk mostly about this structure 1 and methane hydrates particularly. Now, in terms of stability, they are stable, I told you, at low temperatures and high pressures. So here we have a stability diagram, what we call. The pressure is now depicted here in terms of depth, because we're talking where does it occur in nature. So let's just look at depth in meters. And that is our temperature here. As you see, that is the freezing temperature 0. So the first thing you see ice, which is actually stable at higher temperatures than 0. And that's the nice thing about it, up to 30 degrees centigrade, which is pretty warm. But let's take the bottom of the ocean today. The bottom of the ocean in most places is about 2 degrees centigrade. Let's move up here and then go to the left. That's a logarithmic scale. So what it tells us that at the temperature of the bottom of the ocean at about 2 degrees centigrade, we can get hydrates at about 500 meters of water. So it's not very deep. It's quite shallow. In margins, 500 meters of water, whereas the hydrate is already stable. So we do have the right temperature. We do have the pressure because of the water column. What we need is the methane. So we need 3 things. We need the pressure, temperature, and the methane. When we look at the permafrost areas, here we see again, now we have the water and the sediments. We see the same as in the previous diagram. But when we have the permafrost and we have colder temperatures there than we have in most of the ocean, then the hydrates can form already at about 100 meters of water to 150 meters of water. So they can form much shallower, and that is the temperature. Again, the methane is needed. And that explains this diagram. When we look where methane hydrates do occur on Earth, you see it is in continental margins. It's not in the middle of the ocean. It's in continental margins and in the permafrost area, Siberia here, and in the Arctic. That makes a lot of sense because that's where most of the organic matter in the ocean is. Most of the organic carbon in the ocean, 90% of it is in continental margins. That also is very nice because we don't have to go very far from the continent in case it is really an energy source. We don't have to go too far into the deep ocean. So that's where the methane hydrates are on Earth. Now, how much of it is happening and why do we care about it? Because there's so much of it. Here in 1988, Ken Walden, who is a famous researcher on gas hydrates, came up with this type of a diagram. He made the calculation based on the organic matter and the methane production, and these units are in 10 to the 15 tons, gigatons. If that doesn't mean much to you, you know what a trillion is. Trillion is a big number. We're talking about 1,000 trillions, okay? So it's 10,000 trillion, you know, a trillion of tons of gas hydrates. Now, if we look at the area, we know how much fossil fuel we have on Earth, and here we have the coal, just the fossil fuel. If we take all the fossil fuel on Earth, there is more carbon in the gas hydrates than in the fossil fuel. So we are talking about something enormous. Now, recently, scientists have recalculated all kinds of modelers, you know, they change and calculate and do some new calculations, and they come up with different numbers, came up with lower numbers. But even if it is, you know, an order of magnitude less, it still is enormous, okay? The question is, how is it distributed, and why do we care? I mean, it's there, so maybe it's there. Why do we care about it? In the United States, we already know that we have, in the United States, that much. Here we have cubic feet of gas. And most of the things we know now is the Blake Ridge on the East Coast, North Slope of Alaska, Gulf of Mexico, and again in Alaska. These are known deposits of hydrates in the United States margins, and certainly there's much more in the California margin. We also, Northern California margin, we have Oregon, Washington, there are hydrates. All right, so all these hydrates exist. I mean, whether it's 10 times more, 10 times less, it's a lot there. So how is it related to global change? First of all, let's look at the origin of the methane. We need the methane in order to get the hydrates. So the origin of the methane is either biogenic or thermogenic. Thermogenic means the organic matter is being decomposed by biological bacteria, or it's being heated up and forming methane. So these are two origins of methane, and they have their own geochemical signatures. We can distinguish with them very easily. We analyze them because they have carbon isotopes which are very different. So organic matter, the starting organic matter, has carbon isotopes of -20 to -27. So it's very different from that. Now, the other thing which has happened is that carbon-14 of these hydrates is usually already the carbon methane hydrate, carbon-14 is depleted. It's already dead because most of the carbon, the organic matter which is used in this hydrate is old, and the carbon-14 has a half-life of 57-30 years. So after about 35-40,000 years, it's very difficult to measure carbon-14. So it is also not live. If new organic matter has a lot of carbon-14. So it has its own geochemical signatures, which is very important. And these very negative carbon isotopes was used by geologists to trace past events, because how do you know methane once it's not preserved? You don't know what the methane was there. But if we look at geological events, we look at the carbonates which inherit some of these carbon isotopes, and geologists have looked at changes in carbon isotopes to see if indeed in the past the hydrates were related to climate events. Now, here is one example, which is the most famous example, and that is 55 million years ago. It's a boundary between Paleocene and Eocene. I just want to show you, here's an example of, that's the temperature, and that is the carbon isotopes I showed you. Here you see we have the deep sea, and we have the surface ocean. You see what happened at that time. It was a warm time on Earth, and both at the surface of the ocean and the deep ocean, the temperature were very warm. Here we have the deep ocean was as hot as 16, 17 degrees centigrade, and I told you today it's 2 degrees centigrade. So the ocean was much, much warmer than today. And what do we see in the carbon isotopes? We see that at the time that the ocean warmed up so much, the carbon isotope became lighter. And the geologists and geochemists and oceanographers were wondering, what caused this lightening of the carbon isotopes, and they suggested that this dissociation, that there was a lot of gas hydrate because the ocean warmed. Many of them, you saw the stability diagram, did not survive. They dissociated and just released the carbon, which is very light, and they caused this. Now, there's a lot of controversy about it in the literature. It was a very exciting time when this paper by Jerry Dickens came out. But today there are a lot of controversies because there are different ways that carbon isotopes can become lower, can become more negative. So it's not really absolutely clear that that was the case. The reason that they came up with these ideas was because both the surface ocean and the deep ocean, they became more negative. So it means it was a big event that the whole ocean changed its carbon isotopes, which is not so simple to do. But it is controversial. It's not clear that that indeed was the case. But that is a type of things that geochemists are looking for to see the effect of climate change on gas hydrates and what remains, how do we read it and how to interpret it. Another time that people interpret gas hydrate dissociation because of warming was in the snowball Earth. There also was warming there, and they see the low carbon isotopes. So there are these events that people are looking at and trying to interpret, but we should realize it's an interpretation. We really don't have the methane to analyze. Okay. Let's look a little bit about the modes of occurrence of hydrates today. So let's look at the present system, and let's try to see what can we figure out, what can we predict based on our present system and knowing the physical chemistry of the gas hydrates. Now, the mode of occurrence are mostly marine or in permafrost. If we take the amount of gas hydrate in the marine environment, permafrost, most of it is in the marine environment, and that is 5%. But even 5% of a huge amount is a lot. Now, in the oceans there are two types of occurrences of hydrates. Some of them, about 20%, 15-20% of the hydrates are at the sea surface, at the very sea surface, close to the surface, and the rest of it are deep down at the base of the gas hydrate stability zone. The depth of the base of the stability zone depends on the geothermal gradient, what the temperature is. Mostly it's about 200 meters, 300 meters burial, not more than that. There's one place on Earth, it's at 600 meters, but usually it's not very deep, okay, in terms of depth of penetration in the ocean. It's just that depth. What I'm going to show you, I'm going to carry you through now some pictures showing you the occurrence, because it's really, if you haven't seen it, it's amazing to see. And I will show you first the surface, the seafloor occurrences. Here we are in the Gulf of Mexico. You see the seafloor occurrences. You see the methane is bubbling out here. And whenever there is all these nutrients coming up, there's a lot of life associated with it. Like when you have hydrothermal systems, there's a lot of life associated. So these are benthic communities, and they are based on chemistry and not photosynthesis. And I show you another picture of the same thing. You see that's oil here, and there's some mussels here. So there's a lot of life associated with this venting and the seafloor gas hydrates. That is a yellowish one because oil is associated with it. So we drilled a core here from a submersible, and that is yellowish because some oil is associated with it. That's another very, very famous sea surface type of a hydrate, and that is at Berkeley Canyon in British Columbia. And that was actually discovered by fishermen. What the fishermen did, they troweled. Fishermen today trowel a lot. And they picked up a ton of something. They didn't know what it is. They saw something white. And they brought it up, and they saw the ocean bubbling, churning. They didn't know they were smoking. Luckily, nothing happened, on the ship. And one of them tried to be very helpful to scientists. He took a piece and put it in the freezer, in the refrigerator, in the kitchen. Luckily, it wasn't a big piece, so the refrigerator did not explode from all this gas. That was very lucky, but he came back after about an hour and couldn't see anything. It was all gone. It just not stable at surface temperature and pressure. So that is the occurrence of Berkeley Canyon, and I'm going to show you what happens. You see, it needs methane. So when you see something at the surface, that means that the methane is coming all the way to the surface. The moment you take it away from the seafloor, see what is happening to this hydrate. It is decomposing. You will see now, that is at Berkeley Canyon, that is a submersible and a robot, which is picking up a piece. The hydrate is less dense than seawater, so it's floating if you take it away from the seafloor. So you can imagine if suddenly there will be a decomposition of a lot of hydrate, what can happen in the oceanic environment. Here you see floating pieces there because they are less dense than seawater. And you start seeing some bubbling because it was taken away from the sediment, it starts bubbling. And now they're sort of analyzing it by laser. But very soon you will see the fate of these hydrates if they indeed get released from the seafloor or from the slope and start floating in the ocean. So here you see a piece holding, the submersible is holding it and watching it. And you see very slowly it starts to bubble because it was protected by some oil. You see the yellowish part is protected by oil. But you see the bubbling is increasing with time. And very soon you will see still some oil here. And very soon you will see how quickly it bubbles, and eventually it's going to decompose completely. There was a suggestion that the Bermuda Triangle was formed by this gas hydrate in the past. So now you see what's happening here, and that is what is happening. So you can imagine what these fishermen saw when this piece came up. You know, that is the kind of thing that the fishermen actually saw. And eventually, in a very short time, it just disappears, and the methane will be oxidized by oxygen to CO2. Some of it may go to the atmosphere and cause some global warming. So here we are worried that one of the problems is if some of the methane hydrates succeed to decompose, and the methane succeeds to go to the atmosphere, then methane is a very potent greenhouse gas and will cause some warming. The way we study these surface hydrates is by using submersibles or ROV. That's one of my ex-students sitting in the submersibles. They're all waiting in line to go down to the bottom of the ocean. You have to realize when we find these gas hydrates, we can't just bring it up with a submersible because it's going to decompose on the way. You saw what's happening to it, correct? It will decompose. So we need some special containers which are insulated and pressurized in order to bring these hydrates up to the lab and study these hydrates, okay? Now, so these are the superficial hydrates. The other hydrates in the ocean are at the bottom of the stability zone. That is the deepest one in the Andaman Sea, and that is the base of the stability zone. You see here a reflector, correct? You see here we have red above black, and here we have black above red. What that indicates, here we go from water to sediment, we go to the less dense material to the more dense material. Here we go from the hydrates to gas. Down here is gas. So we see the inverse reflector. And that's how geophysicists recognize this kind of boundaries using this inverse reflection. And the hydrate mostly occurs here and becomes less and less towards the top because the methane is advecting from below. So that is an occurrence. But sometimes, you know, to do that, you need a drill ship because you have to go deep. But it's not always nice to be on the drill ship if you have this kind of an ocean. So we don't always have a very pleasant situation at the ocean. Here you see a type of an ocean which doesn't allow you to do very much work. So once in a while, you experience that as well. Okay, when the cores come up, what do we do with the cores? Because we are getting hundreds of meters of cores. So we cannot analyze the whole thing. We are using infrared, and wherever the cores are cold, that's where the hydrates are. So we are not going to waste very much time on that here. We are going to zero in on these places where the hydrate is because we want to pick it before it decomposes. So the infrared is very, very helpful for us to zero in and sample it. And here you see the Andaman Sea. We analyze the pore waters for the chloride, because when they decompose, the seawater becomes diluted, the pore waters become diluted, but you can see that the distribution is from the bottom up, and we have much less here. It's a different types of distribution. You see here also that sediments are not always complete everywhere the hydrate is. It chooses its sediment. When the sediments are coarse or fine, the hydrates like to be in coarse sediments. In this case, these are ash layers because it is near a volcanic arc. So it makes sense because ash layers have more porosity and permeability, or sandstones. So when the hydrates have a choice of sediments, they go into the coarser sediments, which is a very important thing for exploration, to know that. Okay, so you're looking to the coarse sediments. We go to the laboratories and we take the pore water, we squeeze it here, and we analyze for pore water by these squeezers. Okay. Now, you see, here we see some coarse sediments conglomerate in the permafrost. It's totally cemented by hydrate. And here we see a sandstone, which is totally cemented by hydrates. But most of the sediments in the oceans are not coarse-grained, and therefore the question is, where does the hydrate occur? So here you see some nice occurrences of hydrate in the finer-grained sediments. What the hydrate is doing, it needs to grow because it's forming. So it's pushing away some of the sediments aside, and it's just forming this kind of concentrations in the finer grained sediments because it cannot just penetrate in between the fine grains, so it finds its own place because it has to form there. It is in the stability field. So that's how we find it. And here is one case. We are not in the ocean, we are in Lake Baikal. You also see it picked up certain sediments where it's forming in Lake Baikal. So it doesn't have to be in the ocean, but that certainly quantitatively is not very important. So we have seen how it forms, and now the questions are, we know where they form, where they occur. What is the global integrated flux of methane from permafrost and marine gas hydrates? Because global warming is here. I suppose that most of you in the audience here do agree with this statement. Is something already happening? Are they already decomposing to a certain amount in the permafrost and maybe in the surface layers of the ocean, where the heating, the warming up is occurring first? Is it happening or not? We don't know, or do we know? Okay, and then the other question is, what is the potential the contribution of methane hydrate for future climate change? If it's not happening yet, what can we expect in the future? Are they going to play a role in global climate change as a positive feedback? Because if they do decompose and they succeed to go to the atmosphere, methane is succeeding to go to the atmosphere, then methane is a very potent greenhouse gas, as I already mentioned to you before. Okay. So these are the questions that we are asking, and then the question is about, are gas hydrates related to geohazards and landslides as well? Because they cement the sediment, so if they decompose and this cement disappears, can they cause some landslides? So these are the type of questions we have to address, and the question is how to address these kind of questions. Before that, just very quickly, why is methane so important for us? Because it is a greenhouse gas. The radiative impact of methane is about 26 times that of CO2. Okay, so that's why methane is more potent. Is more potent than CO2. Now, in the atmosphere today, the methane doesn't last very long. It gets oxidized by the radical OH. But if there is more methane in the atmosphere, today the half-life of methane in the atmosphere is 9 years, but if there is more methane in the atmosphere, then the half-life increases as well. Do we have some times in the past that there was more methane or less methane? The methane fluctuated really in the atmosphere. And then if we do look at these times, then can we understand the cause of this increase of methane and maybe understand the role of gas hydrates in this fluctuation of methane? I'm sure you've seen these diagrams several times in the series of lectures. That is the Vostok ice cores. Here is today and 400,000 years ago. These are 4 cycles of glacial, interglacial, interglacial, and glacials. we are here today. And what we see here, we have hydrogen isotopes, which are proxies for temperature. That is the CO2, and that is the methane. So we definitely do see that the methane and CO2 behave similarly. And it's very, I mean, today, the argument is no more, is the methane really the trigger of the warming, or is the feedback? It's clearly that the methane is not the trigger, but is the feedback. But once methane is coming up, then the warming can keep becoming warmer and warmer. What is happening today? Here from the IPCC report, we are getting here 6 cycles of glacial interglacial. And here we have from 2001 to just 8,000 years. And you can see that suddenly the methane increases tremendously here. And here it's expanded. It's 2002 to 1986. The methane keeps going up. These are different measurements for different sources, but they all show some increases of methane. So the question is, what is causing the increase of methane in the atmosphere today? It still keeps going. Now, the possible causes of abrupt increases of atmospheric methane, and here are 3 possible causes. The wetlands definitely are producing a lot of methane, and that is assumed to be the most important source of methane into the atmosphere rapidly, because once the climate warms, they expand as well. And recently, that has been added to the list of possibilities. In the Siberia and Alaska, there are these thermocrust lakes, and they produce quite a lot of methane. And the question is about that one. Everybody is talking about these 2, but there is very little discussion about that one, because that is a more difficult thing to measure and to observe. So the question is something happening there as well? Because that definitely is a possibility, correct? There's a lot of hydrate. One of the students of Jeff Severinghaus gave me this slide. It's just a nice slide of wetlands. I thought you'd like to see that. Okay, when we take the IPCC report, what we see here, we see that the sources of methane to the atmosphere today are mostly anthropogenic, and from the natural resources, it's mostly wetlands, as you can see. They don't, in this report, hydrates and the ocean as a source is not considered as an important. These numbers are not very good. These numbers are not very well known. They just report what is known today. So the question is, do we want to know more about it and see if that's correct or not? Because definitely, once you have a total and you have sources that you don't take into account, you have to rethink the rest of it, okay? So currently in the atmospheric methane budget, also they're using the carbon-14 depleted, where there's no more carbon-14, as a natural source. They use that as how much oil anthropogenic input we are producing, and it goes into the atmosphere. On the other hand, methane hydrate and other geologic sources, which are not caused by anthropogenic processes, are also carbon-14 dead. So if these are going into the atmosphere, then this number here in the IPCC is also incorrect. We have to adjust it. Okay, so definitely knowing what is happening in the ocean and permafrost is very important in order to have better numbers for all these calculations and as well as modeling. Now, how do we know the source of paleomethane? Usually we have carbonates and they have the isotopes of the methane, but the best way to see paleomethane is to go to ice cores. The ice cores, they have the atmosphere, and there the methane is, and the methane can be measured, correct? But the ice cores don't go that far geologically, but we do the best we can. So here is a theoretical way of looking at ice cores. If we look theoretically, carbon-14 is decaying. So here we have carbon-14, active carbon-14, new carbon-14. It's decaying, and eventually it's depleted eventually. So that is a theoretical curve with time before present. You see there are no numbers here. It's just a theoretical curve. Now in the ice cores, we do see that at 14.7 there was a warming event, the Berling, and that is the Younger Dryas. Now theoretically, if the warming was caused by some introduction of methane hydrate, and that is a question, do we see in the ice cores the introduction of methane hydrate? This carbon-14 is already depleted, so it will lower the curve, so the curve will not look like the red one, but will look like the yellow one. One of Jeff Severinger's students, Paterno, who did finish his thesis just a few weeks ago, did a marvelous job. He did a beautiful piece of work. He analyzed the methane in these these ice cores. That is a very difficult task. And he came to the conclusion that indeed, by modeling a few percentages of the carbon-14 in the ice cores at these events came from gas hydrates. So that is one step forward, which was very important. Not much, less than 10%, just a few percent, but at least he suggests, based on his interpretation of the data, that some gas hydrate contributed to the carbon-14 at these times in the ice cores. All right, so what fraction of the natural methane production reaches the atmosphere? How do we find out? The main methane sinks are the following. When methane is being formed, either biogenically or thermogenically, what is happening in the sediments before it goes anywhere, the bacteria are utilizing a lot of the methane by anaerobic oxidation. So that is happening all over the place in the sediments. And then some of it, when you are in the stability field of gas hydrate, is sequestered in gas hydrate, and that is a lot of methane. When it comes to the seafloor, you saw the benthic biomass is using some of the methane. And what succeeds to come into the water column, in the water columns there are other bacteria. They oxidize aerobically the methane in the water column. And as you know, the ocean is quite deep at most places. And they utilize oxygen and produce CO2. So the question is, after all these sinks, how much is left to go to the atmosphere? What is very clear that climate change may already, if not, it most likely will impact the sink of the sequestration of gas hydrate, because if the ocean is warmer, the depth range that gas hydrates can occur will decrease, and it also will affect these number 4. First of all, if the ocean is warmer, there is less dissolved oxygen in the ocean, so it will affect at least these 2 sinks of the hydrate. So most likely more methane will succeed to go to the atmosphere. But how do we measure it? How do we do an experiment? How can we go about and give numbers? I mean, we can theoretically say all that is going to happen, but how can we give numbers? So we did an experiment, and where we did it in the Gulf of Mexico. What you see here in the Gulf of Mexico when you dive, you see a lot of seeps, a lot of plumes. That is a sonar of plumes. Some of them go all the way to the seafloor. At the seafloor, some of them have oil. They have some slicks of oil at the seafloor. And when you use satellites, NASA has satellites, you can use, and you can count in the Gulf of Mexico how many of these slicks do exist. And then maybe we can do some calculations if we can determine how much methane is escaping to the atmosphere, because if this plume goes all the way to the surface of the ocean, much of it will go to the atmosphere. The question is, how many of them do we have? How much is coming to the atmosphere today? How do we do it? Okay, how do we measure all that? So we designed an experiment. And a student of mine who is now a postdoctorate is here in the audience as well, Evan Salomon, was responsible to much of the work that we did. So what we did, we used a submersible. Here he is in the submersible. I did some diving, and you see you have to go from the top in. You can't just enter. You don't have a door here. You have to climb up there. So what we did is the following. We went to an area in the Gulf of Mexico where there are a lot of these plumes, a lot of bubbling. You go down there and you see all these bubble plumes. And so we took an area which was known to bubble with all these synthetic communities on the seafloor. And we took this submersible because this submersible has the capability of sampling water from inside. I can, from inside, sample the outside water. So what we did, we took the submersible and went all the way to the bottom. And in this bubbling plume, we were in these bubbles, we slowly moved up and kept sampling the water column to see eventually the concentrations of the methane all the way to the surface. So we got the concentration of the methane at the ocean atmosphere interface as well. So in addition, we took some CTD, some casts, where we analyzed the methane in the vicinity of these plumes as well. So we have the regional distribution of methane in this area. We also put some new instruments on the seafloor, and we measured for a whole year how much methane is coming from the seafloor into the ocean. And we analyzed the sediments, and based on the profiles, we got numbers how much of the methane is being oxidized in the sediments. So we had all the different parts of the puzzle in this region, sediments, and we came up with some numbers. It's just one region that we did this experiment. You can imagine you can't immediately do it worldwide. And what we came that in this region, there was 1 teragram of methane which was escaping to the atmosphere, which is 25% of what the IPCC gives us, and that's just one region. Okay, is already 25% of what they're giving us. So there must be much, much more in the world ocean. When we take the seeps in different areas of the ocean where some numbers are known, we come up with 5 to 10 teragrams, which is 2 times what IPCC is giving as a natural source of methane. Now, when we take all the other geological sources, we're coming up with about 30 teragrams. So we're starting to get some numbers, and the numbers are much larger than we actually have in the literature and in the IPCC report. Okay. In the permafrost region, we also think that some methane hydrate apparently are already dissociating. And the reason that we're thinking that is happening there is the following. When the sea level is low, and these are methane hydrate, the atmosphere is very cold in the permafrost. The ocean is warmer than the atmosphere. If the ocean starts getting on top of the hydrate, then suddenly there's a thermal shock that the hydrates are getting, because the ocean is at least 10, 15 degrees warmer than the atmosphere, and this warm pulse is going slowly into the hydrate, and eventually hydrates have to dissociate. So sea level change in the permafrost is a thermal pulse that causes dissociation of the hydrates. So what we saw up till now is that some methane is escaping into the atmosphere. We cannot say whether it's hydrate or not. It could be just gas, methane gas, but definitely methane is escaping today from the ocean to the atmosphere more than the IPCC is giving to us. And there will be more later on if the ocean becomes warmer. And the permafrost is also impacted, or will be impacted further in the future, when the sea level will keep on rising and the thermal pulse will reach the permafrost. The only thing that I didn't show you now very briefly is what would be the impact of these deep hydrates on landslides. And I will just very quickly go through that, and I will show you that seafloor stability is another concern. Now, before I show you a few slides on that one, you should realize one thing, that methane is, as we say, a very potent gas. Now, it would be great to capture the methane hydrates for energy before it decomposes. That would be the best thing to do. If we don't capture it and we let it to decompose, we first are going to lose some methane that we are not using, and we are going to get some negative impacts on nature. So it would be nice to do a lot of research and try to see if indeed the methane hydrates are a new energy source or not. I mean, there's a lot there, but the question is, how does it occur before they get decomposed? So that is one thing that we need some funds to do that. Now, in terms of seafloor stability, I told you already that they cement the sediments as you saw. And the question is, if by dissociation, the seafloor stability can be impacted. And as you can see, that there are many processes that can trigger failure of the slope. Earthquakes, when there is a steep slope and there is rapid deposition, sea level fluctuations, but also when hydrates dissociate, there's so much gas formed there locally that there is overpressure and it causes some seafloor failure. So methane hydrates could cause seafloor failure. So how do we go about studying that? What is happening is there are many scars of many landslides, huge landslides, after the glacial maximum. The most famous one is in Norway, the Storriga, and that was suggested to be caused by methane hydrate dissociation. It's 8,200 years ago when some warm water came and impacted the slope of Norway, and there was a big landslide. Recent work by scientists who went there again dispute this interpretation. So many of the existing big landslides, scars, these are scars. After you come, a landslide happened, you have a scar. So you have to study the scars. It's very difficult to study scar and reconstruct what really happened. So the best thing is to go to certain areas which have a potential of sliding and study them and see the different properties before they slide and learn about potential seafloor slides in relation to methane. So here and the way to do it is to do some mapping, do some geochemistry to see if methane is really associated in this region, and then eventually monitor these sites. Now, we had a collaborative study with Woods Hole. At Scripps, Neil Driscoll and I were involved in this study. And what the Woods Hole and Neil Driscoll found along the shores of Virginia and North Carolina, they found a large scale of elongated, some things they called glass blowouts. What are these glass blowouts? First of all, I'm going to show you where the area is. We are here in North Carolina and Virginia, and we are talking about this region here. We are talking about this region here. There's a sequence of blowouts which they interpreted to be related with methane. But they didn't have the evidence. When you look at the blowouts, that's how they look like. That is the sea shelf. And you see this blowout, you see the dimension. Something is missing here, definitely. Something blew out. These are large scale. You can see the scales here. That is one of the blowouts. Here you see a second blowout, and you can see it's already filling in. So it happened some time ago that this blowout was filling in. So what did we do? Also, there are some carbonates, oxygenic carbonates associated with these blowouts, and they usually indicate methane, but they didn't really measure the methane. So what we did, we went out and we did the following. That is an AUV, an autonomous vehicle. Here is a methane sensor. And these autonomous vehicles are wonderful. Actually, they have some very sophisticated computers, and they're being they're being told what to do at night. They're being told where to go and what to measure and where to measure. And this one was sent to move around in these blowouts at 3 meters above the seafloor and measure the methane distribution in this region to see if methane is really coming out. We sent it at night, and during the day what we did take some cores, and we took some cast in the water column as well in addition to that, and these are all the cores we took in the different blowouts, and eventually we got some data. And what you see here, that is blowout B, for example, you can see that what these we found was that at a certain depth, at about 110 meters, there is an increase in methane in the water column near the edge of the shelf. And then that happened in all the different blowouts. So when we get an integrated map, here we see water depth from 100 to 160 meters. The depth of this blowout is about 50 meters. So what we see, here we see the shallow parts, and here we see the deep parts of the blowout. And we will take the methane concentration. We see that the methane concentrations are confined to here and not in the deep parts of the blowouts. And we also took some cores, and we came up with the geochemistry that indeed methane is involved in this area. So in summary, I cannot show you many of these results because of the time. In summary, we found out that the active methane venting is concentrated along the upper parts of the blowout walls. So first of all, we identified the methane and also the location of the methane. And the formation of these linear arrangements of pockmarks or blowouts is likely related to trending tension due to downslope creep at the shelf break. So that is an area of potential landslide. So what we need to do now is to monitor this region before there is a big landslide and just have the scar to work with, okay? And big landslides, you know, can be very dangerous, could cause tsunamis and some other things as well. So you saw the relationship between hydrates and global change and slope stability. So what should we do in the future? Really, we have to identify natural gas hydro deposits. Where are the big deposits? Which are the most dangerous ones and are the best for energy? And also analyze the mitigating hydrate-related geohazards. That is something that we have to really understand and predict and analyze. Now, to do all that, we need to develop some new technologies for both, and these things do cost money. The fact is that the US is spending 10 times less money on this research than Japan, for example, or India. So there are so many countries that are interested in it worldwide, and we are not spending enough here in the United States, and we are hoping that in the future things will change and we'll have more because we are getting more evidence of the importance of these gas hydrates for our environment, both energy and maybe hazards. Thank you.